Stars are giant balls of burning gas. These celestial bodies are the powerhouses of the universe, providing light and heat to surrounding planets. They are born from clouds of dust and gas, known as nebulae, which collapse under their own gravity to form a protostar. Over millions of years, this protostar gathers more mass and eventually ignites nuclear fusion in its core, becoming a full-fledged star. They shine brightly for billions of years. During this time, stars undergo various stages of evolution, burning through their nuclear fuel and changing in size, color, and brightness. Some stars, like our Sun, will eventually expand into red giants before shedding their outer layers and leaving behind a dense core called a white dwarf. But even stars don't last forever. The life cycle of a star depends on its mass. Smaller stars burn their fuel more slowly and can last for tens of billions of years, while massive stars burn through their fuel much more quickly, living for only a few million years. When massive stars run out of fuel, they collapse under their own gravity. This collapse is dramatic. The outer layers of the star are expelled in a violent explosion known as a supernova, which can outshine an entire galaxy for a short period. The star's core implodes, squeezing matter incredibly tightly. This implosion is so intense that it overcomes the repulsive forces between atomic nuclei, compressing the core to an extreme density. Imagine crushing a mountain into a grain of sand. This gives you an idea of the incredible density achieved during the formation of a black hole. That's how dense a black hole is. The gravitational pull becomes so strong that not even light can escape its grasp, making it invisible to the naked eye. This cosmic crunch creates a black hole, a region in space where gravity is so strong that nothing, not even light, can escape. The boundary around a black hole is called the event horizon, beyond which nothing can return. Black holes are invisible because they don't reflect light like stars and planets. However, we can detect them by observing the behavior of nearby objects. Stars and gas clouds that come too close to a black hole are caught in its gravitational pull and can emit X-rays as they are heated to extreme temperatures. We know they exist because of their effects on nearby stars and gas. By studying these interactions, astronomers can infer the presence of a black hole and estimate its mass and size. Black holes remain one of the most fascinating and mysterious objects in the universe, challenging our understanding of physics and the nature of reality. Imagine a black hole as a cosmic drain. It has an invisible boundary called the event horizon. The event horizon is like the point of no return. Once something crosses it, there's no coming back. Think of a boat approaching a waterfall. If it gets too close to the edge, it will inevitably plummet down. Similarly, anything that crosses a black hole's event horizon is pulled in by the immense gravity. Not even light, the fastest thing in the universe, can escape the pull once it crosses this boundary. Black holes are like cosmic vacuum cleaners, but on a cosmic scale. They are regions in space where the gravitational pull is so strong that nothing, not even light, can escape from them. This makes them invisible to the naked eye, and they can only be detected by the effect they have on nearby objects. They have incredibly strong gravity, which is a result of a massive amount of matter being squeezed into a very small area. This immense gravitational force pulls in everything that comes too close, including stars, gas, and even entire solar systems. This gravity is so powerful that it warps the fabric of space-time itself. Imagine space-time as a two-dimensional sheet. A black hole would create a deep well in this sheet, distorting the paths of objects that come near it. Imagine a bowling ball placed on a trampoline. The weight of the ball creates a dip in the fabric, causing any smaller objects placed on the trampoline to roll towards the ball. The ball creates a dip in the fabric, and this is a simple analogy to understand how black holes warp space-time. The more massive the object, the deeper the dip it creates. That's how black holes warp space-time. The immense mass of a black hole creates such a deep well in the fabric of space-time that it can trap anything that comes too close. This warping of space-time is what causes gravity. The more massive an object, the more it warps space-time and the stronger its gravitational pull. Objects near a black hole feel a strong pull towards it, just like objects rolling towards the dip created by the bowling ball. This pull is so strong that once something crosses the event horizon, the point of no return, it can never escape. Just like objects rolling towards the dip created by the bowling ball, anything that comes too close to a black hole is inevitably drawn in. This includes stars, planets, and even light itself. This immense gravity is what makes black holes both fascinating and terrifying. They are powerful forces of nature that challenge our understanding of physics and the universe. Their ability to warp space-time and trap light makes them one of the most intriguing phenomena in the cosmos. Time is not absolute. It is a concept that has fascinated scientists and philosophers for centuries. Unlike the ticking of a clock on your wall, time in the universe can stretch and bend. This idea challenges our everyday experiences and opens up a realm of possibilities that are both mind-boggling and awe-inspiring. It can be affected by gravity. The force that keeps us grounded on Earth also has the power to alter the flow of time. Imagine gravity as a fabric that can be stretched and compressed. The stronger the gravitational pull, the more this fabric is stretched and the slower time moves. Near a black hole, time slows down. Black holes are regions of space where gravity is so intense that nothing, not even light, can escape. As you approach a black hole, the gravitational pull becomes stronger and stronger, causing time to slow down dramatically. This phenomenon is not just theoretical, it has been observed and measured by scientists. This is called time dilation. Time dilation is a direct consequence of Einstein's theory of relativity, which fundamentally changed our understanding of space and time. According to this theory, time is not a constant but a variable that can change depending on the strength of the gravitational field and the speed at which an object is moving. Imagine two identical clocks, one near a black hole and one far away. The clock near the black hole would tick slower than the clock far away. This difference in the passage of time is not just a theoretical concept, but has practical implications for space travel and our understanding of the universe. The clock near the black hole would tick slower than the clock far away. This means that if you were to spend some time near a black hole and then return to a region with weaker gravity, you would find that less time has passed for you compared to someone who stayed in the weaker gravitational field. Time dilation is a strange consequence of Einstein's theory of relativity. This theory has been confirmed by numerous experiments and observations, making it one of the cornerstones of modern physics. It has profound implications for our understanding of the universe and our place within it. It means that time is not the same for everyone. Depending on where you are in the universe and how fast you are moving, your experience of time can be vastly different from someone else's. This relativity of time challenges our intuitive understanding and forces us to rethink our place in the cosmos. It's relative to your position and your motion relative to a gravitational field. The stronger the gravitational field, the more pronounced the effect of time dilation. This means that astronauts traveling at high speeds or near massive objects like black holes will experience time differently than people on Earth. The stronger the gravity, the slower time flows. This fundamental principle of relativity not only deepens our understanding of the universe, but also opens up new possibilities for exploring the cosmos. As we continue to study these phenomena, we may one day unlock the secrets of time itself. Section 5. Spaghettification, a long and strange journey. Falling into a black hole would be a very unpleasant experience. As you got closer, the gravity on your feet would be much stronger than the gravity on your head. This difference in gravity would stretch you out like spaghetti. This stretching effect, called spaghettification, would continue until you were ripped apart. Even atoms wouldn't survive this extreme gravitational pull. The light you emit would also be stretched and distorted, creating bizarre visual effects. Section 6. The singularity, where physics breaks down. At the center of a black hole lies the singularity. This is a point of infinite density. It's where all the matter that falls into the black hole gets crushed into an infinitely small point. Our current understanding of physics cannot explain what happens at the singularity. It's a place where gravity is infinitely strong, and the laws of physics as we know them break down. It's a mystery that scientists are still trying to unravel. Section 7. Whirling wonders, spinning black holes. Most black holes spin. They form from collapsing stars that were already rotating. As the star collapses, its rotation speeds up, just like a spinning ice skater pulling their arms in. This spin creates a region around the black hole called the ergosphere. In the ergosphere, space itself is dragged along with the black hole's rotation. It's a bizarre effect that further demonstrates the power of these cosmic objects. Section 8. Black holes glow Hawking radiation. Black holes aren't entirely black. They actually emit a faint radiation called Hawking radiation. This radiation is caused by quantum effects near the event horizon. It's as if the black hole is slowly evaporating. Hawking radiation is incredibly faint. It's much weaker than the cosmic microwave background radiation, the faint afterglow of the Big Bang, but it has profound implications. It means that black holes aren't eternal. They slowly lose mass and eventually evaporate completely. Section 9. Unraveling the mysteries black holes in modern astrophysics. Black holes are still one of the most mysterious objects in the universe. They challenge our understanding of gravity, space, and time. Scientists are constantly learning more about them through observations and theoretical models. By studying black holes, we can learn more about the fundamental laws of physics. We can also gain insights into the evolution of stars and galaxies. Black holes are a reminder that there's still so much more to discover about our vast and mysterious universe. Thank you for watching. If you enjoyed this video, please like, comment, and subscribe. Check out our other videos and playlists for more fascinating content on astrophysics and black holes.